Good afternoon, everyone. Thanks for coming to our next seminar in our series where we attempt to understand some things that go on in the theory of Yang-Mills connections. This afternoon, we're very pleased to have Brad Wilson joining us from all the way from the UK. I believe Brad's currently a PhD student at the University College London. Brad has very kindly agreed to talk to us about harmonic maps and the small energy estimate. Thanks very much, Brad.
Yeah, great. Thanks, Tim. Thanks for inviting me. Okay, yeah, so I'll talk a bit about harmonic maps. Uh, okay, so I guess a harmonic map is essentially a generalization of a harmonic function, um, which is something in the kernel of Laplacian to maps between manifolds. So the way you generalize it is you say that a smooth map is harmonic if it is a critical point for this functional. So it solves the corresponding Euler-Lagrange equation. And here are some examples. So when M is one-dimensional, these just happen to be geodesics, so paths with zero acceleration. And okay, so when N is just Euclidean space with the standard metric, harmonic maps are just tuples of harmonic functions, like I said. And you also have these special cases. So the identity map is harmonic and also the constant map to a point, which will come up a bit later. Okay. So before diving into stuff, let's talk about some motivations of why you would study harmonic maps. So they're related to heaps of different areas in geometry and PDE, but I'll just mention a few. So they've got applications to minimal surface theory. So if a surface has a harmonic Gauss map, then it has constant mean curvature. And if it's also conformal, then the surface is minimal. So that's zero mean curvature. And this generalizes somehow to higher dimensions, but it's a little different. Okay. So there's also this harmonic map flow, which is where harmonic map a map will evolve like in time and eventually sort of flow to a harmonic map. That's sort of the idea. And this has been used in lots of places.
Excuse me,
Even
Brad.
gauge
Sorry to
theory.
interrupt.
Yeah, no
This
worries.
might just be me, but I don't think I see your entire screen. For me, at
Yeah,
least, the
there's a
last
bit cut
bit.
off. I don't really know how to fix that, to be honest.
Oh, okay. Well,
Oh, I can move it to the side.
ah, so how much
Um,
are we missing? Hmm.
yeah, I don't know if I can zoom out. Hang on a sec.
Yeah,
Um,
see if you can fix it, but if it's going to take too long, then don't worry.
yeah,
Uh,
hang on a second. So I can do this, and maybe I can zoom out a bit.
oh, it's because it's in your web browser.
Yeah, but I was going full screen like this,
Um,
but it
okay.
just
Well, maybe it would take too long,
defaults
but
to that somehow.
you could try to open it in like a PDF viewer.
So
Uh,
how many words are we missing in that first point, for example? Okay,
it's
we're
literally just
missing.
like
Okay,
a few letters,
maybe if you keep it there,
which is
maybe
kind
we
of
can
annoying.
cope. Cool.
Yeah, I mean,
Yeah, it's
if
just a
it's
few
important, I'll
letters, I
try to
guess.
like go over to the side.
I guess it adds a bit of spice to the presentation.
Yeah, maybe
Yeah,
if you shift it to the left, and we'll just cope with the extra letter that we miss out on.
yeah, or alternatively, I could just oh, I was gonna suggest I just zoom in here, but I've
Probably
done it
better
so
the
that like
original way. Yeah.
each one has like a new sort of slide to it.
Yeah, maybe it'd be better if it was just back to the old one, and
Yeah,
it's we'll deal with the missing letter.
yeah. All right, sorry about that.
All right.
Okay.
Well,
Okay, what
if you're
else?
able to
So
just shift to the
yeah,
right just a tiny bit, because I know I've got a bit of space on the left-hand side. Or is that going to
yeah.
reset after each slide?
Uh, I think it does.
Oh,
Yeah, but
okay.
I can just keep moving over. Yeah,
Okay,
it's no
sure.
worries. I can just press the arrow keys.
Cool.
Okay, great. So what else? We've got the main sort of thing we're working towards in this seminar, I guess, is the Uhlenbeck compactness theorem. So, well, I mean, what I'm going to sort of start to prove today is the one for harmonic maps, but it also applies to ASD connections in Yang-Mills theory, which is quite important for like compactifying moduli spaces and defining invariants and stuff. And the key feature of this is that as things converge, they form what are called bubbles, which we'll see examples of later. And okay, the last thing I mention is symplectic geometry. So the same techniques work for looking at sequences of pseudo-homomorphic curves, which do essentially the same thing as maps from surfaces, like we'll study. And this is important for a bunch of things in symplectic geometry. Okay, so I defined this functional with this norm here, but I didn't say what it was. So let's just go back to that quickly. We're using the trace norm. So just in general, if you have a matrix, you can do this. And so this is the adjoint map from between the cotangent bundles. And the way you interpret it is by using the isomorphisms induced by the metrics on these tangent bundles, so that this makes sense as a map. Okay. And what are the Euler-Lagrange equations? So we wrote down the energy functional, but these will have some sort of equations where critical points are solutions. So a critical point here is a harmonic map. And probably the easiest way to write them down is to choose an isometric embedding of this codomain manifold into Rn. And then the Euler-Lagrange equation is just the tangential projection of the Laplacian. So this T is the projection onto the tangent bundle of M. All right, and we can go a bit further. We can write it in coordinates. So if nu is the normal bundle of N, then we have this second fundamental form, which probably a lot of people have seen. So it's just the normal part of the Lebesgue connection, like this. And it turns out that the harmonic map equation can be written like this. So it's not just Laplacian f equals 0, like in Euclidean space, you've got this extra term coming from the geometry. So if you write the function as a vector valued thing, taking values in Rn, it looks like this in coordinates. Okay. So what we want to do is construct harmonic maps somehow. And probably the best way to do it is to realize them as limits of sequences somehow. So the idea for this is you want the derivative of this energy functional to approach 0 because the derivative is 0 at a critical point. And also you probably want the energy to also be bounded. So those are the conditions I'm saying here. And such sequences ought to converge to a critical point, although we'll see that they won't always do that. So just in general, if X is a Banach manifold or a Hilbert manifold or something, so this is your space of functions, and you have a functional F like our energy functional. So this satisfies the Palais-Smale condition if every sequence in this function space such that the energy is uniformly bounded and the derivatives tend to 0, every such sequence should have a subsequence converging in this space, and the limit point being a critical point. So this won't always hold, but when it does hold, generally things are nice. And we like nice things in maps, I guess. Okay, so one example where it's nice is the case of geodesics. So if you let this omega PQ be the path space of paths from P to Q in this manifold N, then this energy functional does satisfy this condition. So what this means is if you take a sequence of geodesic paths, or if you just take a sequence of paths, sorry, with bounded energy and derivative of this energy functional converging to 0, then there's a subsequence converging to an actual geodesic. Okay. So ideally, this would generalize, right? So we could take the energy functional in higher for higher dimensional domains, and you would get like a similar sort of convergence to a harmonic map. But it turns out that this isn't true, and the way it fails is quite interesting. Okay, so why does it fail in dimension 2? So one reason is that, well, this is, I guess, the main reason, is because the energy functional in dimension 2 is conformally invariant. So if you change your metric to a scaled version of itself by like some positive function, then the energy with this new metric on your domain manifold M changes like inside the integral by this factor of lambda. And as you can see, when M equals 2, this just goes away and the energy is invariant under this change. So that means if you take a conformal map from your manifold to itself, meaning that it pulls back the metric to such a G tilde, harmonic maps are invariant under composition by this. So one thing you could do is say, just take M equal to S2 and N equals S2 as well, I guess. So then the conformal maps are just Mobius transformations. But this is non-compact because you can have like sequences of dilations going off to infinity, for example. And so you can compose with these like divergent sequences and have sequences of harmonic maps with no convergent subsequence. So this is sort of why it fails in like for the surface case. And it also fails in higher dimensions, but worse. The surface case, because it's this sort of critical dimension which has this invariance, it turns out to be quite interesting. Okay. So then the question is, if this condition fails, how do you realize harmonic maps as limits of a sequence? And I mean, what Sachs and Uhlenbeck came up with was to define this other functional for some parameter alpha strictly greater than 1. They define this on maps as this formula. So when alpha equals 1, it's just the same as the original one plus a constant. So what they did was they showed that this satisfies the Palais-Mail condition when alpha is greater than 1. And we'll call critical points of this functional alpha harmonic. And yeah, that's good because now we can construct alpha harmonic maps as limits of sequences. And basically their idea was to look at what happens to these maps as alpha approaches 1. So you're sort of constructing each alpha harmonic map by a sequence, and then you're looking at a sequence of alpha harmonic maps to hopefully get a harmonic map. But it turns out that you don't usually get just a straight up harmonic map. It'll do some weird stuff. So we saw this before, like that was the situation where all of the maps were harmonic. And they didn't even converge to a harmonic map. So yeah, this is tied up in some sort of Sobolev embedding stuff, which we'll talk about later. And So this is the strategy. Okay, so what was their theorem? So they proved that if M is a compact two manifold and you've got a sequence of alphas approaching one, then if there's this sequence of alpha harmonic maps with bounded energy uniformly, then you can pass to a subsequence and they have some sort of convergence property. So what they proved is that there's like this finite set of points where things go wrong. And so away from these points, you converge to a harmonic map on this complement here. And they also described what happens at those points where things go wrong. So at every such point, there's these sort of limiting maps, which are limits after you sort of blow up, like you rescale around those points. So somehow at these points, the derivative is going to infinity, and the functional isn't well behaved. But if you rescale so that the derivative remains bounded, you get you end up getting this map from a sphere into N. And this sphere is what's called a bubble. And there's also this energy inequality, which is quite nice. I think it might be a mistake there. I'm not 100% sure. Okay. So let's just clear up what I mean by a sequence of rescalings. So that's for these maps Fj. I really should have drawn a picture. Can I draw a picture? Yeah. So basically this is saying that you've got this point Q, which is one of these bad points, and the sequence of rescaling means that like you can find these other points Pij converging and disks sort of around them. Should really be a bit bigger. So these disks, and these scale factors go to infinity. So what this means is that if you compose the map with the scale factor, you get this sequence of maps which are defined on increasingly large disks. So they're filling up the complex plane. And the idea is that they tend to a fixed map from the sphere. Well, a priori, it's just a map from the sphere minus a point, but it turns out you can improve it. Okay, and here's a picture. So if I guess the point 1 is this Q that I was talking about, as you converge, these sort of layers, these disks get blown up into this bubble map where it's slowly like covering the sphere as it converges. So this is the sort of picture you should have in mind. And then this other part here is sort of the rest of the harmonic map. So away from like this point, stuff will converge genuinely to a harmonic map away from those points. So that's this part, and then this is the bubble. Okay. And just a quick example, it's probably maybe too basic to get any great intuition, but let's just consider maps from the sphere to itself given by dividing the identity map by a constant. And these are harmonic. So away from z equals infinity, we see that they just converge to 0. So infinity is sort of one of these bad points. And in the limit, this map extends over infinity to become a harmonic map on the whole thing, just sending everything to 0. So this infinity point is where the derivative sort of blows up and the bubble forms. So as k increases, the maps sort of really try to converge to 0, but small disks around infinity will get pulled over the sphere to form the bubble. And then how do you get the bubble map? Well, you just rescale. So if you rescale by k, you just get the identity. So that's what the bubble looks like in the limit. Okay. So I'm gonna try and start to prove this theorem today, like not in all detail, but a reasonable amount, I guess. And okay, so there's two main ingredients. And the first ingredient is this small energy estimate. So it's basically saying that there's this energy threshold epsilon and some constant such that for any harmonic map from a disk into your codomain manifold with energy less than this threshold, you've got some sort of bound like this. So essentially the derivatives are sort of controlled with how much they can grow on smaller disks. So this only holds in the disk of half the radius. And the second thing is this removable singularity theorem. So this one's quite nice. If you've got a harmonic map from disk minus a point to your manifold with finite energy, then you can always cover over the whole basically and define a harmonic map on the whole space. So this is sort of what we were using implicitly. Actually, I think I forgot to say it. It should say here that oh yeah, no, it does say it. Okay, so basically the idea is that the FIs are converging to F on compact subsets of this, but so a priori F is only defined on this complement, right? But then you use the removable singularity theorem to extend it over, so it becomes well defined on all of them. And then you do the same thing when you're defining the bubble. So a priori these FJs are only defined on, I guess, the punctured sphere, and then you extend them to a map like this. Okay. All right. So let's try and give a proof now of the like Uhlenbeck's theorem, assuming these other theorems I mentioned. So I'm gonna mostly follow Donaldson's notes, mostly because I was also learning this to give the talk. So he assumes that alpha I equals 1 always. So this is essentially restricting to the case of like we're looking at a sequence of genuine harmonic maps and what they converge to. Okay. And I think it's not too hard to extend this generally. That's what Uhlenbeck did. And you just get a lot more constants coming in, I guess, because your harmonic map equation changes when you use the perturbed functional. Okay, so if we suppose we've got this sequence of harmonic maps in with finite energy, you can pass to a subsequence and assume that these integrals converge. So these DFIs are converging as measures. And we're going to define this function. So let x just be a point in M and R a positive number. And then we're going to define this sort of smoothed out characteristic function for this disk in M. So it's equal to 1 over the disk and 0 outside of twice the radius. So I guess probably most people can visualize this, but it's something like you've got the disk here. Your function is 0 outside, and then it jumps up to 1, and then it goes down again. And it does this like in every direction. Okay. Okay, so we're going to define some functions. So let mu of x r be this limit, which exists because of the convergence property I mentioned. And mu of x is the limit as r goes to 0 of this thing. So this mu of xr is I guess it's increasing in r. So as r goes to 0, it's decreasing. And I guess sort of the idea is that this mu of x is capturing what happens to the integral as this indicator function approaches a delta function. Okay, so for let's just fix an epsilon, and we'll deal with that later. Define this set. So this is points in M such that this mu of x is greater than this threshold. So in some sense, this is the set of points where things go bad, because when mu of x is greater than some positive number, you've like your derivative, this term in here, is growing fast enough to counteract the shrinking of this part as r goes to 0. So in some sense, this should be the set of points where your derivative blows up. And okay, so what next? Then we've got this inequality, right? So for every r, every point in S epsilon satisfies this. So this energy, the limit of the energies over this disk of twice r is bounded below by epsilon. And okay, so if we take a finite set, then the goal of all this, by the way, is to show that S is finite. So let's take a finite subset and choose R such that it's sort of partitioning the manifold into disjoint balls. So you've got your manifold like this, and you've got these points, and you're just choosing the radius of these disks so that they don't intersect. So that they don't intersect. Yeah, like that. Okay. So then you've got n copies of epsilon on 2. You're just using this inequality on the previous page. And because all the disks are disjoint, this is less than the total energy of Fi, so it's less than this maximum threshold. And then this implies that this number n of points in our finite subset was actually bounded above. So like S epsilon can't be infinite, because then you can always just pick more points. Okay, and what's going on now? So we're assuming the small energy theorem, right? So if we choose an epsilon like we had in the small energy theorem, and let S be that S epsilon, whenever mu is actually less than this threshold, so i.e. these are the points which should be well behaved, because we had greater than before, right? To define S epsilon, we're doing less than now. So then you get this upper bound instead. So this limit of these energies are bounded from above, and then you can choose small enough r and large enough I so that this is true. And so this is the energy of Fi over this small disk, and then you apply the small energy estimate. So because it was independent of the disk, right? Up to like a factor of the radius. So the energy, sorry, the derivative of this particular Fi is less than a constant. And this will apply for all I further along in the sequence as well. So what you really have is uniform bounds on all of the derivatives on this complement. And so by the Asel-Rascoli theorem, these should converge to a harmonic map on this complement. So that's one part of the theorem done. And as I mentioned before, you've got a removable singularity theorem, which lets you cover up the holes. Okay. So then the next part was about bubbling and rescaling. So if you take one of these bad points where things are blowing up, by what we just did, you know that these derivatives aren't uniformly bounded on small open subsets around the point. So there's some like neighborhood of this Q where the derivative is large. And on this neighborhood, it will assume some supremum. So let's say that occurs at the point pi and call them maximum lambda I. So then if we rescale these Fi's by the lambda i's, we'll get a sequence of harmonic maps defined on increasingly large disks with bounded derivatives, because now we've renormalized so that the supremum is less than 1. And because they have bounded derivatives, we can apply exactly the same thing we just proved to show that they converge to a harmonic map from the sphere. And furthermore, we know that this isn't constant because we constructed the map f to have derivative 1 at 0. Okay. Are there any questions at this point? No? Okay, great. So now I'm gonna try and prove the small energy theorem.
Actually, just a question.
Yeah, sorry.
Can you go back
Yep.
one?
Yeah, which slide? This one?
Yeah, this one, first paragraph.
Sure.
Size of DFI achieves its maximum. We're going in to a critical point, aren't we? So
Yeah, that's
why does that actually achieve? Why does it? Why doesn't that blow up to infinity? Why does it achieve its maximum?
So the idea is that it is blowing up to infinity, but as I goes to infinity. So
okay. So
the picture is something like this. So you've got this disk around Q, right? And if you were to plot the norm of dfi as a function, maybe it goes something like this, where this here is your pi, and this is norm of dfi. But the point is that as you move closer in, these supremums get higher and higher, going to infinity.
Yeah. Okay. I mean, I was actually thinking that the limits that you took, limits of I and R that you were taking earlier on.
Yeah, it's a bit. Yeah, there's a lot of limits going on.
I had a slightly different picture of what you're doing, so I thought each of these maps were having singularities at the
yeah. No, I think
at the points
yeah,
Q.
because each of these Fi maps, they're genuinely harmonic. So they won't have any bad behavior. We're just looking at what happens to them in element.
Okay, thanks. I had forgotten the definitions. Thanks a lot.
Yeah, no worries. Okay. Okay, so the small energy theorem. I think this might be kind of confusing. It's I found this really confusing to learn, and I'm not sure I've learned it 100%, but we'll give it a go. So the basic idea is to first assume that we have so I'll use this notation for the Sobolev spaces. So this one down here is the regularity. So the amount of weak derivatives, I guess. And this is the integrability. So the power you're using in the LP norm. Okay, so the basic strategy is to show that if you have an L2 alpha 1 bound, I guess that's how you say it, on F, so you're bounding a first derivative in the 2 alpha norm on this disk, for some alpha greater than 1, that's important. So if you've got this bound, then you want to show that it implies these sort of bounds, so L2 alpha bounds on F over a slightly smaller disk. And then for reasons that we'll see, we'll be able to use this over and over again to get bounds on the derivatives of F on smaller disks. Okay. But that's not really the situation we wanted to be in, because we wanted to assume that the energy was less than some threshold, right? And the energy is just the L2 norm of dF. So maybe the L2 norm squared, I guess. Yeah. So what I've said here fails in our case, because we have alpha equals 1. Right? Because we're in L2, not L2 alpha. So what we need to show is that with this small energy threshold, you actually do get an L2 alpha bound with alpha greater than 1 whenever epsilon is sufficiently small. Okay. So with this one up here, you could show that this bound here implied this bound, no matter what this bound was. But down here, it has to be sufficiently small for it to work. Okay. Yeah. I'm not sure how much of this I'll get through actually, but since I'm giving another talk on this removable singularity theorem, I might just, if I don't have like time to finish or whatever, I'll just overflow into that, I guess. Okay. So the first step is to translate the domain, the codomain n, so that the integral over this disk of your function is 0. So you can do this just by like translating so that the center of mass of your image disk is the origin, I guess. And we've got a harmonic map equation. I talked about this before. You've got this second fundamental form, and a priori it doesn't really make sense, because like these are one forms, not vector fields, but you're just translating between the two with a metric. Okay. And so let's let this chi be a smoothed characteristic function for a slightly smaller disk. So you're taking a very slightly small disk d prime, and chi is going to be the smoothed characteristic function to that vanishing outside of d. And you have these identities. So if you took the Laplacian of chi f, so chi is just a function, you'll get something like this. And the second fundamental form also satisfies this identity, which comes from the Leibniz rule. Okay, so I guess this is a bit of a commutation. So if you want to bound the norm of this Laplacian pointwise, you can first use the triangle inequality in Cauchy-Schwarz. Then you plug in this sort of a priori bound. So we're assuming here that f is harmonic. So it satisfies the harmonic map equation. So delta f equals like minus a of df, right? And so we're plugging that in and using the other formula. You expand it out a bit, and essentially you get this by using like the continuity of the second fundamental form as a bilinear map. And c is just a constant. So I'll use the convention that whenever I write a little c, it's just a constant depending on, I guess, just the geometry, which can only change line to line in the equation. So you get some sort of bound like this, right? And c depends only on this characteristic function. So I've absorbed like some norms of like derivatives of chi into there, for example, like this thing, this, and we can do that because chi is just a smooth function. Okay. So then we want to suppose that alpha is greater than 1 to prove our implication. And we're supposing we have some sort of bound on the L2 alpha norm of the derivative. And I'm putting a question mark here because we'll determine that later. Okay, so using the Cauchy-Schwarz inequality and possibly Holder's inequality, you can get this. So this subscript alpha here is just this is the L alpha norm. And when I write like this with the 1, that's the L1 to alpha norm. Okay. So you've got some sort of inequality like this, and we want to show that we have a L1 alpha norm, no, L2 alpha norm. Okay. And that's on the next slide. So right. So now what you do is here you have just elliptic inequality because the Laplacian is an elliptic operator, and we then use what we just proved, and finally we can use okay, so I guess we're using a Sobolev embedding theorem here. So this this F alpha, you've got some sort of embedding like L2 alpha into L alpha because your manifold is compact finite volume. And I think, yeah, here we're using the Poincare inequality because we assumed that the average of F is 0 at the start. So, right. And so now there are two cases, basically. So if alpha is less than 2, we have this Sobolev embedding. So L2 alpha going to L1 beta, for beta being this thing. So 2 alpha on 2 minus alpha. And this provides an L beta bound on this derivative of chi f on the disk D. Yeah. So this gets improved to an L beta bound on df on d prime. So d prime is the smaller disk, and this just works because you can always bound this below. Well, we're saying we can bound it below by Will there be another constant here? And chi f, and then we're doing, well, I guess d chi f, and then beta norm, and then we're further bounding that below by the norm on L beta of d prime. So this is the norm with respect to L beta of d, and then because d prime is a subset where this chi is equal to 1 on d prime, you just get f. You just get df in here. Okay. So we've got a bound like that in terms of this this original bound we had. Remember, this is coming from above by question mark, which we'll sort out later. And okay, so then the important part of the argument is basically that because beta is greater than 2 alpha, right? So this is greater than or equal to 2 alpha, because alpha is less than 2. We can do this again with alpha prime equals to beta over 2. And so we improve this L2 alpha bound to a L2 alpha prime bound, i.e. an L beta bound, and beta is greater. So this is improving our situation. And what's the second case? So the first case was, remember, alpha is less than 2. And in this case, alpha is greater than 2. So here we get an embedding into this Holder space. So whatever that is. But the important part is that you get a bound on df pointwise in terms of this original L2 alpha bound. So let's see that. So we're using this inequality again, which I proved a few slides ago. And right. I guess I didn't explain how this works. 1 second. So on the previous slide, we had this, right? And what I'm saying is that you can bound this below by like this Holder norm. So some of the terms are like sub f over d, and then you'll also, because it's a C1 something, you'll also get a sub df in there, also over d. Except these should really be chi f and d chi f. But then in the same way as before, these are bounded below by the subs over d prime, because chi is 1 on d prime. So you're saying on smaller disks you have this, and there's also an extra term coming from the Holder derivative, whatever it's called. But the point is that you get a pointwise bound in terms of this original L2 alpha bound on the derivative. Okay. And then sort of the final part of this thing, before we actually go on to prove the theorem, is we use this inequality again to get a L alpha bound on the second derivative, say, over a smaller disk again. So d prime is sort of changing. I'm using like heaps of different smaller disks. And we just repeat this process again to get bounds on higher derivatives. So I guess this is a bit confusing, but the basic idea is that so on this previous slide, we could sort of increase alpha, right? So we started with an L2 alpha bound on df, and then we got a L to alpha prime bound on DF as well. But like I guess alpha prime is strictly greater than alpha. So we can increase alpha until it passes 2. And when it passes 2, we're in this other situation. From the next slide. So when alpha becomes greater than 2, by doing this process, we can finally bound the derivative pointwise. Okay. Hopefully that made like a bit of sense. It's quite confusing. Okay, so now the question is basically, I'll wrap it up quite soon, I think. I just want to put this into context. So now the question is, how do you actually get these L2 alpha bounds in the first place to improve to bounds on the derivative? Because we needed alpha greater than 1, right? That was important because otherwise we didn't have the Sobolev embeddings. And yeah. So basically the idea is to take E of F small enough so that this L2 bound given by this equation actually implies this other thing. Okay. So remember we had this inequality pointwise. Actually, do I want to do this now? It's not actually that long, but I might stop here actually if the cutoff time is strict, because I don't think I have enough time to finish this little bit.
How much extra time do you think you'd want?
Oh, like 5 minutes.
Well, we did start late. I'd be happy to give you the extra 5 minutes.
Yeah, sure. Okay. We can do that then. Okay, so we're trying to choose an epsilon so that this works. So we have this inequality for the Laplacian, and the idea is to yeah, so if we choose some alpha in this range, so and set beta equal to this again, we have this thing holding. So this alpha is going to be the thing we want there, right? So we've got this, so we can use Holder's inequality to get something like this. So here we're keeping this term. In the previous one we threw it away. So yeah, we've got this, and there's some constants C1 and C2, and we do something similar by applying the elliptic inequality, a Sobolev embedding, and the Poincare inequality, and it just reduces to this. So we used the elliptic inequality to get rid of the Laplacian on this side, and it's now been replaced with this, also using the Sobolev embedding. So we've got new constants, C3, C4, like this. And the important thing to realize is that this term and this term are exactly the same. So what we can do is we can rearrange this equation so that they're all on one side. And okay, I've just put the same thing at the top there, but basically if you choose square root of epsilon to be this, so involving this C3 constant, whenever you have the norm of df in the L2 sense, so this is just the energy, right? Whenever you have the energy less than epsilon, you can rearrange the equation so that this is true. So derivative here is less than this term, but this only has L2 bounds, L2 norms, and we can bound those because we know that this is true. So we do exactly the same thing as before. We pass to a smaller disk, and we get a bound like this, and then setting what was it? I guess alpha prime equal to beta over 2. We get a L2 alpha bound, L2 alpha prime bound on df, which is exactly what we needed to apply the previous iteration process to get the pointwise bounds on derivatives. And yeah, it was important that epsilon was chosen small enough because otherwise you couldn't do this rearrangement inequality thing. Okay, and then this is just what I said. And that's the end of the proof of the small energy estimate. Okay, I think I'm done.
So in the previous slide,
Yeah.
you warned us, I think, that the C's change from line to line. So the C4 in the middle equation is not necessarily the same as the C4 in the top equation. So
that's okay. So this is the one case where I'm actually not using that rule. So
the same C4.
So in this, yeah, like this is the one part of the argument where the constants are actually important, I think. Because yeah, essentially what you do is you take this over to the other side, so you get a 1 minus like norm of df to C3 there. And yeah, essentially you're just choosing epsilon so that when this inequality is true, you get this bound.
Hello, Brad. How are
Oh,
you?
hey, Brian.
Maybe.
It's good to see you again.
Follow the later development. Is there any notion of a modular space of a harmonic surface, like a harmonic map from 2D? Because is there any something?
I don't know. I guess I haven't really studied harmonic maps too much. Like this is all I know about them basically.
Okay.
So probably. I mean, you get sort of moduli spaces of pseudo-holomorphic curves, which are quite similar, right?
But here is more general. Here your target can be any.
Oh yeah, definitely. Yeah, this is more general.
The one that maybe there are notions of just what do you mean by harmonic modular space? Do you need to fix some topological data just in any modular space? Oh, okay.
Yeah, possibly.
Yeah, I was late. I was picking up my kids from school, and then probably like 10 minutes later. Yeah. Okay.
Yeah.
Maybe I will look at these. Asking some question later, just in case.
Yeah.
So, Brad, sorry about my lack of clarity here.
Yes. No, that's my
theorem,
bad if I didn't explain it properly.
No. What theorem? I'm looking at Donaldson's 2022 preprint, the work of Uhlenbeck.
Oh yeah.
That's what you're following?
Yeah, that was let me
what theorem? You're not proving the Shane-Uhlenbeck small energy theorem, are you? Is that right? Are you proving a Uhlenbeck 1977 result? Or?
Yeah, that was what I'm trying to prove, except in a slightly less general setting, because they had these maps, these functionals E alpha, like the perturbed energy functionals. But all Donaldson proves it for is for when all of the alphas are equal to 1, and that's what I'm doing as well. I'm not really sure how it works in general.
So which is that Donaldson's paper there? Donaldson's.
Donaldson's paper. Let me find where he's actually written a theorem. So I'm proving theorem
3-3.
3. Yeah.
Okay, so that's 4-3 is 4-3 is the Shane-Ulenbeck small energy. 3-3 the reference 57 or not? 3-3 small energy.
Yeah, that's right. And
Which
the
is
statement of the main theorem is theorem 2, so the page before.
yeah.
That's
So
like, yeah.
is a reference for that Ulenbeck's 1977 paper?
Yeah, there's quite similar statements. So this
Yeah.
is Ulenbeck's paper here. I don't know if you can still see the screen share.
Yeah. I'm confused about.
Yeah. Yeah, so basically Ulenbeck did something a little different to Donaldson, and they proved essentially these estimates, which are quite similar to what I ended up doing, I think. But
I thought
so
that
yeah.
Yeah, section 4 is harmonic maps in higher dimensions. So it's 4-3 that's the Shane-Ulenbeck epsilon regularity result.
Oh, right. No, I haven't looked at this, I think.
Yeah, where 3-3 is, what's the reference there? Yeah, I'm not sure. I thought it might have been reference. They give us 57, which is Ulenbeck's 1977 paper regularity for a class of nonlinear elliptic systems.
Oh,
I'm wrong there.
So the paper I'm reading is existence of minimal immersions of two spheres, which I think is where all of this like bubbling stuff sort of invented.
Yeah.
I'm not 100% sure about that, but I think.
Okay, I'm not sure.
Yeah.
Maybe just in case, another question about the bubble of sphere. Does each time carry some minimum energy away, or could be the energy can be lost, can be arbitrarily small?
I think they can carry energy away. So
it's not like it has to be a minimum energy. If in the instant and in some other case, when you're bubbling off, they always carry at least a minimum energy away.
Yeah. I think that is true here as well, actually. There is some sort of energy gap theorem.
Okay. So that means if you fix some energy, then you can compactify by adding the sphere bubbling.
Yeah. So I think you can do some sort of bubble tree in this setting.
Yes. Okay.
Yeah.
But just curious whether harmonicas map from sphere has minimal energy, or maybe I don't see any topological constraint to prevent the energy be arbitrarily small. I just don't see this straight away.
I swear I read that somewhere.
Okay.
So
maybe in this paper.
We're talking about harmonic maps of the two sphere into the arbitrary manifold capital N. Which
just the bubble. Sometimes the bubbling off can the energy lost in the bubbling process be. So that means if you lost, you will stop after finding the final step.
So I think what might be happening is like you've got like the conformal automorphisms of a sphere, I guess, acting in the same way as like the gauge group would. So there's some symmetry you need to like push out by.
Yes, but if we quote that one, I mean the energy should be invariant, like conformal invariant. Yes.
Yeah. That's why the surfaces are best to study. I guess.
In the homomorphic case, because whenever you have homomorphic map, the energy is bounded by a topological constraint, like essentially the L2 norm of the derivatives is equal to the, because the d bar is 0, so you're left
Yeah.
with the
Yeah.
energy is given by the topological data. Like I mean, in the harmonic, in the holomorphic map, you have this like C1 of the tangent bundle. You have a first-chain class of tangent bundle, which is like give you the energy. They like energy achieve the minimum certain condition. I don't see the condition here. Maybe some other way of get to the minimum the energy
Yeah,
gap somewhere.
I could be misremembering what I read as well. It just seemed like the similar sort of thing.
Yes, I thought there was a very close analogy between the harmonic map two-dimensional bubbling case and the Yang-Mills four-dimensional bubbling case.
Yeah, there definitely is.
Conformal invariants. Basically, conformal invariants tell you the bubbling two sphere. In that case, the bubbling four sphere is some same idea, same.
All right, we probably better leave it there.
Okay, thank you, Tim,
Yep.
for organizing this.
So let's
Yeah,
thank
thanks.
Brad for giving us a nice talk on these harmonic maps.
Thanks, Brad.
And
When should
yes,
we talk, Brad?
there'll be an opportunity, I'm sure, to ask Brad some more questions when he gives us his second talk. We haven't specified an exact date for that yet, but maybe it will be in a couple of weeks.
Yeah, sounds
Awesome.
good.
Thanks for coming, everyone. Hope you enjoy your weekend. Brad, I hope you enjoy the rest of your Friday.
Yeah, thanks, Tim. You
See you
too.
next
Enjoy
time,
your weekend.
everyone.